Alright, we're in business. It's level 3 statistics time. I got a comment saying I should do this, and so like, why not? Let's go for it. I actually sat this paper, it was pretty wacko, but I don't really remember much of the answers, so I'm going to redo it. A bunch of writing is generally all garbage. False positive and AI writing is incorrectly identifying fully human written text. 1% false positive rate. 74% of the time it fails to detect AI generated writing. It's pretty useless, isn't it? So 22%. Okay, so 120 times 0.22 should be. What's the calculator right? Bring it up. There are 26.4. We'll say 26 AI, 94 non-AI. Of the 26 AI, it's 1 minus. There's 26 AI generated pieces of writing. 26% will be generated as being AI detected. Cool. So this is 6.76. And of the 94 non-AI, you'd expect 1 from non-AI to get detected. So probably about 8. So it's about an 8. So 7 out of 8 chance of cheating. I think this is how you do it at least. I mean, I have rounded a few numbers here which could stuff up the count, but there's for every 8 people who are flagged, 7 of them were actually cheating, 1 person probably wasn't. So yes, they cheated. I mean, I guess this is where you go on the big ramble. Statistically, it is, yeah, that's good enough. Independent of each other. 1% of students cheat on the assessment. 20% of students complete the assessment in less than 25% of their at a time. I assume 1% is negligible compared to all students. It's pretty tacky of NZQA to but paper about cheating. Then. So probability of finishing in less than 25% of the allocated time times probability of cheating is 0.2 times 0.1. That doesn't equal 0.8. And this makes sense. You know, people cheating finish quicker at a much higher proportion than people who judge. So, not independent. That should make intuitive sense. You know, if cheating affects time it takes to finish the exam. So it should be of no grand surprise. Oh, and interpret your answer. Oh, this is it. This is the interpretation. I mean, I don't know what I think. Okay, whatever. Who cares? That is the interpretation. You just say people cheating will logically finish quicker at a much higher proportion of people don't, so they're not independent. Proportion of cheating to people assessment listed. Estimate the proportion of students across New Zealand who cheat and complete the assessment for the standard in less than 25% of the time. So 1% cheat, and of that, 80% do it in less than 25% of the time. So 0.1 times 0.8 is 0.08. That should make some sense. No, this is probability cheating. Oh, no, that's not right at all, was it? 0.01 times 0.8. That should be probability of cheating times probability that cheater finished early. That's right. Okay, how is this advised? One teacher's course. Based on the logic from one school for a particular NCEA standard. Okay. One school doesn't. I would expand on this. One school doesn't expand. Doesn't reflect on all schools. For example, Auckland Grammar is a much different school to the local random school. And so therefore, one school's cheating records will not be the same as another ones. And reason two, this was for one. I don't know why I'm writing this with my hand. One particular standard. Doesn't reflect. So this was just one NZQA standard. So this might have been level 1 mechanics, level 3 electricity, level 2 horticulture, who cares? They're all different, and so some higher portions may cheat, they may be more difficult, maybe require cheating. Maybe they're a shorter paper in general. I don't think question 2's over. Question 1's over. Oh god. I remember this question being awful. So this is a 3-circle Venn diagram. But shit, how difficult though. 7 applicants have no skill. Okay, so this is coding, maths, domain. Okay, 21 had coding skills, or 21 here. 16 had mathematical and statistical knowledge. 6 applicants had the necessary subject-specific understanding. 6 in this circle. One applicant had only subject-specific understanding. 7 applicants were good candidates for the role as they didn't have any subject-specific knowledge. So they had the other 2. So 7 goes here. So I've used this, this is simultaneous equations. Okay, let's make some variables. We'll go A, X, Y, Z, omega, W. Okay, so I've put some variables in here. The first equation should be 7, well no, actually, A plus X plus Y should equal 14, and that's coming from these things in this circle here. So this plus this plus this plus this has to equal 21 because there's 21 coders. So this plus this plus this must equal 14. 16 applicants with mathematical and statistical knowledge, which means that Y plus Z plus W must be equal to 9, because these 3 plus 7 must equal to 16. 6 applicants are necessary subject-specific understanding. So X plus Y plus Z should equal 5. So these guys plus 1 equals 6. 9 had exactly 2 of the 3 main skills, so that's X plus Z equals 9. I don't know, I don't think it's enough to solve the system just yet. And out of those with one main skill set, So 3/8 had only mathematical and statistical knowledge. So 3/8 of one skill set is 1 plus A plus W, and that should equal mathematical and statistical knowledge. So 3 plus 3A plus 3W should equal 5W. Okay, there is enough information, I think, to solve the system here. We have 5 variables and 5 equations. Okay, if x plus z is 9, I'm going to change the color. If x plus z is 9, then I can replace this x plus z here with 9 and get y equals 4. No, this isn't right then. Something's gone wrong. X plus z should equal 2. X plus z should equal 2. Yes, apologies for that mistake. Because x plus y plus z plus 7 equals 9. So x plus y plus z equals 2. No, what? Hang on. Oh, x plus z plus 7. I guess this equals 2, which means y equals 3. Which means that z plus w equals 6, and x plus z equals 2, a plus x plus y, a plus x equals, what was y? Y was 4, right? 3, okay. This is 11. God, this is unbelievably tacky. I'm just going to put this in a matrix solver in my calculator, and I suggest you guys do the same. So, what you want to do, simultaneous, 1, 2, 3, 4, there's 3 unknowns, is there? A, X, Z, and W. 4 unknowns. 4 unknowns and 4 equations. Alright, 4 unknowns. 1A plus 1x 0, 0, 11. 0a plus 0x plus 1z plus 1w should equal 6. 0a plus 1x plus 1z plus 0w should equal 2. And 3a plus 0x plus 0z minus 5w equals minus 3. And that gives a equals 9, x equals 2, z equals 0, w equals 6. So we can fill in this table now. I will say this is ridiculously hard. What is that? X, Y, Z, right? So this is X, Y, Z, this was W, A was 9. Did these add up? Should add up. Oh, no, this doesn't add up. Oh no, that's gone wrong. Oh, it does add up. I'm just blind. Okay. That was, yeah. The reason they're allowed to do this is because simultaneous equations is technically a standard in statistics, although it is often done in calculus. How many applicants were selected for the shortlist? The shortlist of people with all 3 skill sets was created. Okay, all 3 skill sets. 3 people. Right in the middle. Who had only one of the required skills. 1 plus 9 plus 16. It's claimed that those applicants with the required mathematical and statistical knowledge, applicants are twice as likely to have subject-specific understanding. Get to coding skills. Right, if you have mathematical and statistical knowledge, then 3 out of 16 for M, and for coding, 5 out of 21. 5 subject-specific, 21 coders. So 3 out of 16 divided by 5 out of 21 will get you will get you 63 80ths. So no, only 0.7875 times this. Roughly. Okay, I'm going to zoom back in. Ow. Based on the data, oh wait, there was a graph here. I don't think we can answer this question, yeah, because where's the graph? It looks something like this, and I had like, it was a bar graph. But, oh well. Oh, well this is useless as well, we can't do that question either. There's no, yeah, we can't do these questions unfortunately because the graph's not there. Okay, the dice question. People seem to hate this, but whatever. I would suggest memorizing this. This is the table of probabilities of certain dice rolls. So if you roll 2 dice, the 1, 2, you can't roll a 1. But 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. 7 is this, and I think it just symmetrically tables off either side. And you can prove this with some ability skill, but so this is the odds of rolling a certain number if you roll 2 dice. So for example, rolling a 2 is 1 in 36 because you need to roll 2 ones. I don't know what this is doing. Wins at least once. Okay, well, to answer this we should really ask the question, what's the probability you lose everything? What is the probability you lose everything? Okay. So, probability you lose everything is probability of a loss equals the odds of rolling a 2, a 3, a 4, 11, or a 12. Because any of those rolls makes you lose the game, that round, right? So odds of it, so we've got a 36, this is the 2, 3, 4, odds of a 4, 5 to 10 inclusive, we want the odds of an 11, and the odds of a 12. This is the odds of losing, so 3, 6, 8, 9, 9 and 36 is a quarter. So odds of 3 losses equals 1 out of 64. So then at least once. 63 out of 64 is the chance of winning at least once. Now I'm going to refer to this table for this next question as well. This is sort of like the casino game craps, if you've ever heard of that before. To calculate the probability that the game is lost before the player has to roll the dice for a third time. The probability that the game is lost before the player has to roll the dice for the third time means that can happen two ways. You can lose on the first roll or you can lose on the second roll. Probability lose first. Well, to lose on the first roll, you'd have to roll a 2, 3, 11, or a 12, which, remember, is 1 over 36, plus 2 out of 36, plus 1 out of 36, 2 out of 36 for 11, plus 1 out of 36 for 12. And that's 6 out of 36 for a sixth. But what's the probability that you lose on the second roll? Well, you'd have to make it to the second roll. Right? Okay. So, to make it to the second roll, you have to not lose and not roll a 7. So really it's 1 minus the probability of losing plus probability of rolling a 7. These two, like, if you lose, which is this, or if you roll a 7, the game ends. So to continue onwards, the probability of going through, shouldn't put an equal sign there, probability of going through to the next round is 4/6. But what's the probability that you do that and then lose on the second roll? Well, to lose on the second roll, you'd have to roll a 7. So, times a sixth. So, if successive roll, the player will negate the point to roll again. Okay, so probability of lose on the second is probability you get through to the second round times probability you lose on the second. So that's 4/36 or a ninth. And so we can add these up. So 6 plus a ninth equals 1554. What's 9 54? Yeah, 1554s. We divide that by 3. 5, 15, 16, 17. 5 17s? No, 5 18s. Yes, 5 18s. For these 1,000 rolls, which is more likely, rolling 3 or less or rolling 4 or more? Probability 3. Probability that you roll less than 3 equals, okay, well we're going to go 138 plus 189 plus 197, 524 out of 1,000. So it sort of follows that probability probability x is greater than or equal to 4 should be equal to 476 out of 1,000, because those two must add up to 1. So clearly that's more probable. Should the player probably. I mean, that's far too low, that's far too low, that's far too high, that's good, that's too low, that's too high. This is where you just say experimental probability approximates the unknown true probability. The model probability is theoretical probability of an event. Given the experimental probabilities are quite far from the model, this suggests the true probability is not near the model probability, and hence the dice may be dice. Chance of throwing a total of 2. Well, the true probability of rolling a 1 seems to be lower than model. So getting a 2 is more infrequent. That makes sense, right? If it's harder to roll a 1, then you're not going to get 2 ones in a go. Oh, that's it. We're done.